My name's Martin Pratchett. I'm the Engineering Practice Manager at Engineering New Zealand. What we're looking at today is P21 bracing and their roles in SED structures and some of the things that you should consider. And so what we're going to be talking about is, this is about the guideline that's now on the Engineering New Zealand website, and I'm unsure if it's on the TDS website as well. But it's why we wrote the guide. Things to keep in mind, some P21 and NZS 3604 background, some common issues that we are seeing, and some tips and tricks that, that you can use. And so back in 2021, Auckland Council approached me, and the reason was that they had some problems with engineers designing buildings like these ones using your P21 bracing systems, and they needed some help with that. You know, were these acceptable or not? And P21 tested bracing systems are, you know, designed and used for use within an acceptable solution, like 3604. But the thing is that engineers are using these P21 tested systems as if they were designing using material standards like the timber standard. Now, the thing is that those P21 systems, if they are being used within the bounds of 3604, then 3604 is designed for houses, and they're 1 or 2 stories. And when the standard was written, the intent was around standalone houses, not townhouses or joined units. This was 10 years old, and speaking to you know, a couple of the authors of 3604, then they said, yeah, look, you know, those building types weren't really around then. They certainly weren't common. Medium density housing wasn't coming out, and we hadn't considered that. It wasn't inside the scope of the document. And so my general question for you is, well, we're looking at these buildings here. As you can see, these were submitted for consent by engineers. And are these examples of 1 or 2 story standalone houses? Be quite interested to see if anybody thinks that that's the case. And so what is the intent of 3604, right? It's for designing houses, as we said, and primarily standalone houses. And those houses are expected to be reasonably symmetrical in their bracing around the X and Y axis. They're supposed to have regular bracing lines. They're supposed to have, you know, similar amounts of bracing in each line, and 1 or 2 stories high. They're expected to have a floor area of around about 90 to 150 square meters, right? That's the types of buildings that were looked at when they were doing the document. And in there, you know, they're expecting that those types of houses will have multiple redundancies and alternative load paths. And so when you're doing the designs, these are some of the things that you have to keep in mind, right? And so we've got to say to ourselves, why was it occurring that the engineers were starting to use these systems and embrace, you know, outside of the scope of NZS 3604? And one of the things is the rise of medium density housing, right? And so NZS 3604, it wasn't designed with townhouses and medium density housing in mind. It's why one of the reasons why the standard is being updated. But there's not really anything in there, as far as I'm aware, that explicitly states that you can't use it for that building type, right? And so there's a lot of different building housing types going up now. Long, narrow, multiple units, you know, as I said, they just weren't common 10 years ago. And there's always been a lower perceived risk for residential work, right? And so that means that, in my experience, there has not been an emphasis on providing guidance for those types of buildings, despite the fact that it dominates the construction industry, right? So if we look at the types of building consents that are granted, then typically, you know, if we look at the last year, for example, around about 50,000 building consents were issued. Of those, around about 80% were issued for residential work. You know, so that's houses, right? And so you can pretty easily see that is the bulk of the of the building typology that's being constructed. And as far as I'm aware, universities, polytechnics don't, focus on the various aspects of residential construction. And I don't remember having seen any residential focused seminars by technical societies until the Timber Design Society by Valter, with the sorry, I already said the Timber Design Society webinar, which was, specifically started to address these points. Most of the seminars and so on that I've ever attended are really looking at your medium to high-rise buildings, and it's a similar sort of lack that we've seen with, industrial buildings as well, warehouses. And so there's a lack of guidance documents that have been produced because of, a lack of research, across this type of stuff. And so the first one that I'm really aware of inside here was, SR337, and that was authored by Angela Liu at the request of the EQC after the Christchurch earthquake, looking into the causes of damage, and why there was getting so much damage in these residential houses. And after that, Engineering New Zealand produced a design for residential portal frames because, to try and reduce some of the complexity that was coming out of SR337 and standardize some of those approaches. But there hasn't really been anything that's been out there moving through the issues and some of the potential solutions as well. And so, floor diaphragms, for example, are they rigid or flexible? Well, we always used to consider them as rigid, but actually, if you look at the behavior and that they've started testing now of a floor diaphragm, lightweight timber frame floor diaphragm inside the lightweight timber frame buildings, they behave in a more rigid manner. So our assumptions and so on were wrong and that. And for a lot of these people, there's been for a lot of us doing this type of work, there's a lack of in-depth knowledge on the engineering basis of 3604. Part of that is just because of the fee pressures and so on that we're under. And, and also a lack of understanding of what the potential implications are when we alter these P21 bracing systems, right? And part of that is, sorry, I've just realized that I haven't been clicking to keep up. And part of that is, as a general lack of understanding that a P21 bracing system is designed as a system, right? And so what that means is that you cannot change any part of that system without altering its fundamental characteristics. And so as soon as you do that, you might put in a different, hold down bracket or whatever else it might be. You're having unknown failure modes. You don't know what is going to happen, for the strength, the deflection, failure modes of those types of things. And if we look at it, if you're starting to extrapolate some information, then, with longer walls, then the failure modes start to change. And so here's some things to keep in mind, right? And so as engineers, when we design buildings, we're trying to reduce uncertainty. And the way that we typically do that is by using, the various standards and methodologies, BM1, as an example. And please correct me if I'm wrong, because I would love to know. But as far as I'm aware, we can't accurately measure the factor of safety in a building, right? We can produce these calculations and put in the factors of safety as much as we like, but we don't actually know all of the characteristics that are inside that building. We don't know the construction, things that problems that we haven't seen, and what are the actual material properties and so on. Material, we have to remember that computer models are inherently incorrect, and they can really only provide approximations, right? They are just a mathematical representation of assumptions. And so when we design using material standards, we have to understand, that the characteristics are based upon the 5th and not the 95th percentiles of test results for strength, stiffness, and looking into the demand. And while we don't know the true characteristics of any individual piece of material, we're working to minimize the uncertainty by reducing unknowns. But that's not so much true for P21 tests. These aren't tested in the same way, right? And so when we're looking at these systems, there's less testing, and the average of 3 results is used. And so there's more unknowns, right? So when you use them outside of those boundary conditions that we're looking at for, you know, with those assumptions of 3604 that we saw before, you're increasing the uncertainty that you're designing with. And everything that we're trying to do is trying to reduce that uncertainty. And so you can't make some of those same assumptions. You know, you can't say, okay, well, I've got these characteristics, and so if I add a few more screws down here, you know, in my P21 system, then that should increase this, and I can calculate out the individual, you know, strength of the screw or the nail the same as you can with the timber design standard. It is not the same. It's not applicable. And so that's my little part of the discussion. And so those are some of the background thoughts to keep in mind. And now what I'm going to do is hand over to Mike, because Mike's been working. He had a lot of input into the document itself that we produced, and he sees these sorts of issues on a day-to-day basis, and he is going to run through some of the common problems that they've been coming up against and how they've been working through them. So Mike, over to you.
Yeah, thanks, Martin, and hi everyone that's joined us today. I'm going to start off with a little bit of background. I think, as Martin mentioned, the information isn't always readily available to designers as to what how these tests have been developed and how they're intended to be used. So starting off with the P21 test, this basically involves sort of lab testing of a single isolated bracing wall, and that bracing wall, as you can see in the image on the screen there, that's built in the same way that it would be in a house. So all your hold down brackets, your sheathing materials, your screw patterns and everything all have to replicate the element that's being installed on site. One little kind of unique factor in the P21 test is that it has these supplementary end restraints, as you can see on the image there. Roughly 4.5 kilonewtons worth of additional support put onto the end of those walls. And this is really just a way of representing some of the effects that you would have when the wall is installed into a house. So you've got generally got lintels above window openings, portions of wall which have continuity below windows. There's a lot going on that basically isn't represented in an isolated test like this. So this is just a way of accounting for those effects. It's a system test, so it's looking at how that system behaves as a whole. So as Martin mentioned, if any changes to that system, even though they may seem relatively minor, they can have an impact on the bracing rating that you would receive from that test. The test itself is set up on a rigid foundation, so there is no contribution of the support flexibility, like if that wall was sitting on a timber joist in reality in a real design. You would get some flexibility coming from that support condition at the base. That's not picked up in this test. It's basically a rigid support condition at the base. And the test itself, a load's applied to the top of the wall, cycled back and forth and incrementally increasing displacements. And the bracing ratings derive from the mean value of 3 tests generally. So the sample size of that test is really not big enough to do any kind of statistical analysis on it and come up with a characteristic value. You'd have to analyze a large suite of tests, I think, to really have any accurate attempt at approximating a characteristic value from this. So the bracing ratings that we get, they're generally, they can be extrapolated out to a wall, which is 2 times the length of the system tested. So product suppliers will publish a range of bracing ratings for different wall lengths. And in terms of from that test, in terms of the behaviour that we observe, there's probably a few things worth keeping in mind if you're ever designing with these. We basically get a hysteresis plot of the load deflection behaviour of that wall. And that's representative of what's happening to that wall as a whole. It doesn't really tell us much about the individual components contributing to the behaviour of the wall. If we compare this with when we, say, do elemental design on a plywood shear wall using verification methods, we typically consider every single deformation node within that wall. We'll consider the nail slip, sheathing stiffness, axial shortening and lengthening of the chords, elongation of hold down brackets, and we quantify each one of those elements. We then typically choose a ductile mode of deformation, which is generally, for these types of walls, a nail slip mechanism, and we capacity protect all the other elements and modes to make sure that we're just confining that ductile behaviour to the desired failure mode. Now, in P21 elements, and kind of contrast, there are many sources of ductility, so we're not necessarily capacity protecting any one part of the system and confining the ductility to the nail slip or the screw. The interaction between the sheathing and the timber framing, and we don't really know where this ductility is coming from and how much of it can be attributed to each mode. So we just need to be a little bit careful when we're trying to then apply that to verification method designs. And some things to keep in mind. The P21 elements generally do exhibit a rocking mode. So if we look at the figure on the top left there, if, on the left-hand side, we have a rocking deflection, which it might not actually activate that nail slip mechanism or screw slip mechanism in the element. Whereas generally when we're used to specifically designing walls, we're more looking at the shear type deflection on the right-hand side there, whereby we're getting this nail slip mechanism between the sheathing and the framing. And the response that we get in those hysteresis loops, you can see in the diagram in the bottom, they're a very pinched loop. So we're getting quite low energy dissipation if you think about the energy dissipation being the work done, the area enclosed within those loops. And that's quite low in this instance compared to what the ductility assumptions and reduction factors you would use in NZS 1170.5. They've been derived from much fatter hysteresis loops with a lot more energy dissipation. So that needs to be kept in mind when making any corrections for specific engineering in these systems. And when these rocking modes become dominant also, we have a scenario which is shown by the image on the bottom left, where the dashed line represents what was recorded in the test, the load displacement behaviour. A lot of this was coming from rocking in that instance. Up to 70% of the deformation was just purely rocking at the base. The actual mechanism that we generally think about when we're designing these walls is kind of represented by that darker line. So you can see there that the actual sheathing mechanism that we like to think we're designing for has only been tested to a deflection of just beyond 10 millimetres. And there's already some strength degradation occurring in that wall, anywhere beyond sort of 5 or 6 millimetres. So we just need to be very careful of that and, think about how is this wall actually going to behave if I put it in a system and provide some very strong hold downs to it whereby it can't rock like it did in the P21 test. So there's a question there as to whether we're introducing brittle failure modes into our designs. And that needs to be thought through very carefully. We'll just move on to the next slide there, Mark. Cheers. So these systems are used, the P21 systems are used in the context of 3604 design. And some of the characteristics of those structures, they typically have significant structural redundancies, a lot of walls within the system that are non-bracing walls, but they are there and they do provide some stiffness and strength, even though we don't account for them in our calculations. And we get these continuity effects, which are attempted to be captured by the supplementary end restraints in the P21 tests, but in reality, specifically, especially if you're putting these elements on a ground floor of a 2-storey building, those continuity effects and additional hold down effects can be quite a bit greater than what the P21 test would suggest. And these system effects, I mean, they vary greatly depending on the plan of the building, how open it is, how many of these continuity effects are present. But yeah, from a lot of the research that's been done, it seems like 1.5 to 2 times design capacity could be achieved once you factor in all these additional system effects. So in my view, what we're doing there by designing for the mean strength of the P21 tests and then not taking account of all these system effects is we're essentially building in, those system effects are essentially building in the factor of safety. You can see the shifting of the curve in the diagram there from the mean results up to being more in line with a verification method 1 design that we would do. And I think that sort of makes sense because there is broad acceptance that the performance objectives of the building code are being met with 3604 structures when these system effects are present. You know, typically at SLS level loads, you're getting only minor cracking, nothing that would prevent structure from being used. And at ULS, although there's a lot of damage, generally does maintain structural stability and gravity support of the structure. So I think the key takeaway there is that these system effects are really key to actually making 3604 structures behave more in line with the performance objectives of the New Zealand Building Code. Next slide, thanks. There are some exceptions to those performance observations from testing. There have been some room testing done where a full-scale room of a 3604 type structure has been built and then racked back and forth to look at how it will behave as a whole house essentially. And while the 3604 construction, which then supports those bracing elements, has shown to have some deficiencies, potential weak spots. It's just important to be aware of these doing specific design. In some cases, the bottom plates of bracing elements had fractured, where typical detail where you have a bolt 100 mil from the end of a bracing element and a strap under the bottom plate. You can actually, that cantilever of that bottom plate could fail much sooner than would be expected. The timber floor structure itself, so in a 2-story building, if the joists, if a bracing wall is landing on joists, those joists aren't, well, there is no definition in 3604 of how those joists should be then connected to their supporting structure to follow the load paths through to ground. So that's just something that needs to be thought about. And failure of blocking and joists supporting bracing walls. The load paths, once again, in 3604 construction aren't always followed through well. So basically, on the whole, don't just expect that 3604 type construction will resolve your loads. Actually follow the loads through the building and make sure there is a way of them getting out of the wall into the supporting structure and down to the foundations. Next slide, thanks. So we've just got a few common issues that we encounter day to day in design, which I think are worth sharing. And we're not providing a step-by-step guide of exactly how you could tackle these problems, but just highlighting the key things to be thinking about. One of the common things we see more in modern architecture, modern houses, is just a distinct lack of redundancy compared to a 3604 type structure. You have a lot of these modern buildings have a lot of glazing, floor to ceiling glazings, which pops the lintels up above the top plate and have discontinuities in the top plates. And bracing lines, which are spaced at more than the 6 metre centres that you would normally have from a 3604 type house. And so all of these features basically start to diminish those system effects that we discussed on a previous slide. And the assumption that just following the 3604 bracing methods starts to fall over a little bit. We no longer have that 1.5 to 2 times assistance from the system effects, and need to think a little bit more carefully about how much bracing we're putting in there. And in this case, to account for those effects, we would need to start making some adjustments on the capacity side, and actually start thinking about providing strength reduction factors to the capacity to ensure that they're behaving more in line with the way we'd expect them to behave if they were installed in a 3604 building with all the redundancies. And there's not much research or guidance on this particular point. So this needs to be approached with a little bit of caution, and quite a bit of thought needs to be given to where you're deriving your bracing ratings from, and how much they account for those system effects and material variability and things, and make the appropriate adjustments. I think on this one point is that you could look at this and say, right, we could design that to 3604 though, and you can. It would be technically compliant if you had a floor diaphragm over there, or a ceiling diaphragm with the acceptable solution. But I just say, just because it's compliant with the acceptable solution doesn't mean it's going to perform as well as you'd hope. So just keep in mind the performance of the system, in addition to just achieving the minimum bracing ratings. Right, moving on. Next up. And torsional response, as Martin mentioned earlier, diaphragms, particularly floor diaphragms in light timber frame buildings, they do tend to act more like rigid diaphragms than flexible. And the past assumptions have been that we just do a tributary width assignment of actions to bracing lines. And that's not always going to hold true if you've got a well-proportioned diaphragm. It will behave more like a rigid element. And that's especially true when we start introducing in specific design mass timber floor systems. So CLT, PLT floors, they're very rigid, and definitely need to take account of that in the design. It has a significant impact on the distribution of the loads to the bracing walls. So as a guide, I mean, we're familiar with this as engineers, rigid diaphragm. If we know the stiffness of these elements, we can then account for the eccentricity in that system, and derive the loads from that. Working at the stiffness of a P21 element can be a little unclear, but I mean, as a guide, you can go to the P21 report and look at the initial stiffness of those tested elements to give you the relative stiffness of the walls. And in terms of controlling torsion, I think it would be sensible to limit the torsion to the torsional sensitivity limits in 1170.5. This is basically a point at which the torsional effects start becoming very unpredictable if we push beyond that. So I'd suggest that those limitations that are there and we're familiar with, we can stick to those. Another sort of common issue, which was touched on by Martin, is the displacement compatibility between different elements. So we consider the same example we had on the previous slide, but now we've got a moment frame to open up that elevation architecturally or whatever the reason. We need to give consideration to the deflections or the target deflections of that moment frame in relation to the other walls in the system. So Brand's SR337 gives some guidance on that, and just kind of generally accepted a 1% ultimate drift is appropriate for this. At those level of movements, of course, those steel frames will likely still be in the elastic range. So we need to account for that in the design actions, and make sure that we're taking account for the fact that a large portion of the resistance in that X direction, as it's shown on the page, is coming from an elastic frame. And medium density housing. This is probably the area that I think has caused the most confusion for designers recently. Just as medium density housing has become more prevalent around the country, changes in city plans and whatnot, it's becoming the way of the future. And we've got a situation where naturally designers and builders are trying to apply cost-effective residential building systems which have been developed for NZS 3604 structures. They're trying to apply them to these new type of building, and it's not always a perfect fit. These systems, in my opinion, need to be adapted somewhat to be suited to this type of construction. So basically, the characteristics of a medium density house, you would have typically on the ground floor or the lower floors, you'd have open living or garage spaces. They're almost like a tunnel effect where you've got intertenancy walls on two sides and very little opportunity for bracing through the middle of the building. So even if you did have enough walls to technically resist the shears that you're designing for, there's a real lack of system effects here. So there's going to be a hugely reduced capacity to those elements compared to what you would get from a 3604 design. Diaphragm effects. So if you've got two in a 3-story building, if you've got 2 stories of floor diaphragms, you will get that torsional effect as you go down the building, and probably importantly, these effects are cumulative down the building as well. We sort of mentioned before that there's some known deficiencies in 3604 construction when it is applied even to 2-story buildings. So if we were to then take that theory out to 3 stories, we're just amplifying those risks to the point where I just don't think they're acceptable. So it's really essential just to follow the critical load paths through the building, make sure that they can be resolved. Right, so just got a few design tips here to try and pull together some of what we've covered. In the context of the 3-story building that we were talking about on the last slides. Let's start with the loading demand. Well, this is familiar to us. I mean, NZS 1170 to derive the loads. Nothing special here. We know the mass of the building. We can make an approximation of its stiffness. Selection of ductility is an important one to give some consideration. If you on these systems, you're often mixing frames and shear walls, so you need to select a ductility that's appropriate for the material. One thing to keep in mind is that earlier slide which showed the potential strength degradation in plasterboard walls at quite small displacements. Yeah, you want to think about that when you're choosing your ductility. Is it really acceptable to push these walls up to a ductility of 3? Probably not. I'd be limiting it to a lower level than that. And also when we're looking at these structures, you want to try and limit vertical irregularities in the cases where you have very open ground floors and potentially quite stiff bedroom type layouts in the floors above. Just make sure we're not introducing any weak stories or vertical discontinuities there. Right, so in this case, if we look at, once we worked out our loads, we can start to look at what sort of structural system would we put to this building. In the top floor here, I don't have a plan to show this as a sample building that we had, but there's numerous walls at 3 or 4 metre spacing, very reminiscent of NZS 3604 type construction. So I'd say it's would be a reasonable assumption, given that the system effects are in play, that you could use bracing, P21 bracing elements at this level. Although I would personally design for a lower level of ductility, just knowing that some of these have some inherent brittleness to them beyond 15 to 20 millimeters of displacement. At level 1 in this building, we've got some open plan living down one end and bedrooms at the other end. So it's quite an irregular plan. With that diaphragm there, we're likely to get some torsional effects. So that you need to consider the torsional effects there, the displacement compatibility of any steel frames and walls you're putting in. Yeah, so in this case, a suitable system for this particular building would be some specifically designed bracing walls mixed with moment frames. And then on the ground floor, it's a big open plan, no real opportunity for any wall system. So there would just be a specifically designed moment frame. In terms of the load paths that we talked about, I think it's really important. What I would be looking for if I were reviewing one of these designs would be that the designer has really clearly defined the load paths from floor to floor. In the case shown on the left-hand side there, you may have a bracing wall element which is landing on a joist. That bracing load has to get out of that wall, be distributed through the diaphragm into another frame which might not necessarily line up below that wall. So basically, as we mentioned before, the load paths for that need to be followed through. There needs to be a clear definition of how the load is getting from out of the wall and into the ground, from point A to point B. I'll suggest providing a hierarchy of strength for any brittle elements. So if we're talking about flexural failure of joists underneath those walls, as the walls try to bend from their supporting joists, a level of robustness should be designed into those joists to make sure that we're not introducing any potential brittle failures to the system. And as mentioned before, verifying the capacity of the diaphragms. If a bracing wall dumps a bunch of load into the middle of a diaphragm, you then have to verify that that diaphragm can actually take that load and distribute it to other load resisting elements. So on the capacity side, as mentioned in the previous slide, P21 elements, they do seem like a reasonable assumption for the top floor. There's a lot of redundancy there, and the axial loads are low. So I would suggest that we could calculate the capacity of that floor using P21 bracing ratings, but just give some thought to the level of ductility and performance you would expect from those walls. At level 1, this is nothing unusual once again. I mean, this is 3604 and 3404, just verification method 1. Methods that most structural engineers will be familiar, or all structural engineers will be familiar with. So nothing special there. Same with the ground floor. That's just specific design. The key thing I think to point out here is that the transition between using a P21 type system, say in a top floor, and then taking it into the specific design system below, the interface between those two probably isn't always well considered, and that's just something to look out for. So that sums up what I had to talk through. I think Martin will open it up for questions.
Martin, you're on mute. Daniel, I believe that you are taking over here to do some quick Q&A, is that right? Or I'm happy to read them out if you're not available.
Thank you very much, Martin and Mike, for your thorough and very interesting talk. Obviously, you have made significant effort and spent quite a lot of time to get this project becoming a reality. Really enjoying, and a lot of information to learn. So just wondering, like, if there is any opportunity, maybe few might ask as well, if your presentation PDF can be uploaded together with the recording, if that would be possible. Martin?
Yeah, no problem.
Very good, very good. Having said that, I will pass on to my colleague Daniel to take on for the questions and answers. Thank you very much.
Good afternoon, everyone. Daniel here. Thank you, Namir, for hosting this webinar, and obviously Martin and Mike for putting together this information. There's a lot of interest. We have about 500 participants today. And I have to say we have 32 questions, most of them very long, some very detailed. So apologies, we won't be able to answer all of them. And also none of us will be in a position to answer your specific question to your specific project. This is due to liability and other issues. So we hope you understand that. So it's ultimately your engineering judgment. So Martin and Mike, I will go through some of the questions, summarize them up a little bit. Some are repetitive, so perhaps I start with some common questions, and then we can dig into some a bit more detail. So first of all, a lot of engineers or listeners were asking, considering that P21 might not be appropriate for some of the buildings, could we ask suppliers like JIP and Carterholt to actually provide characteristic data from their bracing systems? What's your thought on that? Maybe, I don't know if Mike, you want to start, and then Martin.
Yep. I mean, that would be one way of addressing the vagueness of the information within the kind of framework of the material design standards that we use. So if we had design data on all of the components that make up a system in the same way that we do in 3603 for, say, a plywood shear wall, then those methods could be applied in a more consistent manner, for sure. I'm, as far as I'm aware, the availability of that information is not there at the moment, but it's definitely something that I think we could we should aim to push for.
Yeah, well, Winston Wallboards was involved with the conversations and getting out the methodology behind the article and the guideline that we all put together. And as Mike said, we actually discussed that inside the group. And as he said, there's not the data there at the moment. It might be there in the future if Winston or other plasterboard manufacturers or whoever else it might be choose to release that information or feel that it's appropriate or whatever it might be. But at that point, it would need to be included in a material standard. And so, is that going to be which standard would that be? Would we have to write another one, for example? There's all sorts of questions around that.
Yeah, I think some more work would be done. And as you say, what standard do we use to define this data is probably the first question. My opinion would be if someone wanted to use a plywood bracing wall system, no testing is required. We know all the properties of plywood and the nails which fix the plywood to the studs, so that shouldn't be a big issue here. There's more questions popping up as we go. There's one question about, or several questions about, rigid versus flexible diaphragm. And I think, Martin, you made a comment about some data which came from the brands testing. And here the question was, you mentioned we always thought that diaphragms were rigid. There seems to be testing which has shown that they behave rigidly, so we were wrong. So I think—
Sorry, other way around.
If you can just clarify.
Did I get that right? So if I said rigid, then I misstated. When I was working as an engineer, then we had always thought that they were more flexible than they were, just as Mike was saying, during his part of the presentation. And so we had looked at them traditionally as being able to assign a tributary area to that. But from testing, and I'm sorry, I'm not sure if the test results have been released in a report yet. Mike might know, but from conversations that I've had with people at brands, then I know that there has been and possibly is still testing undergoing, and it seems like those, there are very rigid characteristics of those diaphragms. And so, yeah, it doesn't look like we can treat them as a flexible diaphragm. You can't just assign a tributary area. You know, your assumption should be that they are behaving in a more rigid manner.
Mhm. Thank you, Martin.
I
There's
think
another.
sorry, just to add to that, in my experience as well, when we've attempted to quantify the rigidity of a diaphragm, I mean, if we were to look at an elastic model of just a piece of plywood in plane, and look at the stiffness of that, you would have to reduce its stiffness down by a very, very long way through, you know, accounting for the effects of nail slip and everything in the diaphragm for it to start behaving like a truly flexible diaphragm. So I think there are some simple design checks you can do that pretty quickly show you that that rigid assumption is a fairly good one.
Mm-hmm. Thank you, Mike. And there's not, excuse me, there's another question still related to diaphragm where I think the Brand's light timber framing guide was cited. So being a coder, I probably can answer that. Yes, the assumption is the diaphragms are rigid in there, but there's also an explanation provided. And because you need to provide a stiffness to the wall, one simplified approach would be to provide the length as a stiffness indicator. The fact being that the shear stiffness and the splices of the nailing, essentially it's all proportional to the length, and therefore the stiffness is proportional to the length. Mike, in one of the slides, has, however, shown also how you can estimate or guesstimate a stiffness out of a P21 tested wall example, if that's what one wanted to do. So another question I need to go through here. I'm picking one of the more specific examples, and perhaps one of you could answer. So here, a listener is asking about the use of P21 or 3604 data on an IL3 building with 50 years design life. The building is a one-story high standalone structure with well-distributed walls. What is your thought about using P21 on an IL3 structure of this type?
Well, if you're looking at an IL3 structure, then it's unlikely to be a house. 3604 is designed to be used in houses.
Mm-hmm. Mike, anything you want to add to Martin's comment?
Yeah, I think, and if that's, I agree with Martin, and if we were going beyond that, then as I sort of mentioned in a couple of my slides, once we start pushing beyond the scope of 3604, we need to start taking account of some of the other factors like selecting more appropriate ductility and accounting for characteristic strength values rather than mean values and things like that. So I don't see that being a simple scaling up of 3604. It requires a bit more thought.
Thank you. Now, going back to the other or initial discussion we had about using characteristic data when designing bracing walls, one listener is wondering or suggesting to use the Appendix B of 1170, which essentially lets you use prototype testing. Could that be approached to define the more characteristic-wise or the more appropriate design strength of a JIP or other proprietary bracing wall system? Is that something which has been discussed in a working group? Or did it come up?
I think we did discuss that. I can't remember what the conclusions were.
I think it sounds like a valid approach, but using one of those methods to make those adjustments. I guess the issue that you find is with such a small sample set, the factors that you would have to put on that uncertainty become very severe. So I think if we were going to start putting doing some probabilistic analysis of the results, we'd want a bigger sample than 3 tests to work with.
Yeah, and I agree with Mike, and thinking about it, as I said, everything that we're doing, we're trying to reduce uncertainty in our designs. There's a famous quote, which I can't remember exactly what the quote is at the moment, but it says, we've got materials we don't wholly understand, and to shapes we can't realistically define, and to modeling that we, in ways that we can't really understand. And all of those things are there, right? And then we're trying to introduce more uncertainty with untested systems being used outside of the scope they're really designed for. And then we're probably going to be altering those in some other ways as well, right? And so all that we're doing there is increasing the uncertainty rather than decreasing it, right? We should be working to decrease the uncertainty is my general approach on this.
Correct. I agree with you for sure on that, Martin. Another case sample which I quite like because it's probably becoming more common. So the question was, there's a house building with a CLT floor. For the rest, it is a very traditional house typology. Can you still use P21 or 3604 for the bracing design, or is the presence of a CLT floor pushing this whole structure into an SED design? So maybe something for Mike to address.
Yeah, I think the presence of a rigid diaphragm straight away means that the bracing line method is no longer valid. So that's probably the obvious one. Beyond that, though, if in the actual wall system itself, if you had all the system effects present, with a lot of internal walls and whatnot, then probably stands to reason that you're going to get a similar performance on the capacity side of the walls. It's just the force that they may experience might be a lot higher due to the torsion in the diaphragm than what 3604 would assume, say, for example. Yeah.
But if I can summarize, so you're saying as long as the demand is determined by a rigid diaphragm, then using the P21 capacity could still be applied.
I think that's reasonable because as we mentioned earlier on, your factor of safety, if you like, in these systems comes from those system effects. So it does stand to reason that if those system effects are present, then you're going to get a similar performance. So yeah, I think that seems reasonable. Just need to be very careful about making an honest assessment of those system effects and make sure they are actually there.
One of the things, I'd like to reiterate what a point that Mike put in there on one of his slides is about stating everything in your design features report, right? Put all of your assumptions in there. And so if you've got that CLT building in there, CLT diaphragm, say, okay, well, we've got a rigid diaphragm. This is the way that we're going to be looking at it, but we have those system effects present because of these things, and so Mike spoke of, and you'll be able to get the information out of the slides, we've got multiple walls, we've got, unused bracing, we've got this, we've got that, well, if those other criteria are met, as Mike was saying, then you've still got some system effects in there, but you've got to make sure they're still there, otherwise, once again, you're reducing your or you're increasing your uncertainty, reducing your factor of safety.
There's a specific question which, Mike, you raised the fact that using stronger hold down brackets in a building might have negative effects on the ductile capacity of the system. And the question is, can you explain a bit further? Because can a jib handy brake actually achieve the 12 to 15 kilonewton hold down capacity, and why would you then, so are you suggesting we should still keep using the jib handy brakes rather than a stronger bespoke or a stronger capacity handy brake? So maybe if you can elaborate that a bit further.
Yeah. Okay. So probably important to point out that not all P21 bracing systems experience the strength degradation at low displacements that I was talking about in one of those slides. So it may be
cycle to the slide.
Yeah, probably not a bad idea. So this was the one with the observed behaviour, I think, of the test. So yeah, so there may be some systems which don't experience that kind of degradation that you're seeing in the black line in that figure there, and it may be that those are those are suitable. You could upgrade the brackets on those without doing much harm. I do think it's a little bit risky to make those kind of decisions off the P21 test like this, though. You probably want to understand a lot more about it. The other thing is that the hold down brackets most of the time they won't develop all of the strength needed to hold the wall down. That will come from somewhere else. So that'll come from, you know, the wall engaging with another perpendicular wall, axial load from the floor supported above. All of these things can contribute to suppressing that rocking mechanism. So while the P21 test, the element rocked while it was on the P21 rig, when you actually put a whole lot of load on that and then tie it in other forms, that may be forced into more of a shear deflection type failure, in which case you're activating that sheathing mechanism much sooner than the P21 test would suggest. So I think it just needs to be a really careful assessment of the racing system that's being used, and making sure if you were going to strengthen any part of it, that you really know how that system behaves. And
I've got a slightly different answer to Mike on that one, and that as I was saying before, those systems are tested as systems, right? And building upon what Mike was saying, if we change a part of that system, we can no longer understand what the potential failure mode is. And Mike's just spoken about 2 or 3 different ones. We don't know what the failure mode anymore is. If you put in that stronger bracket, you don't know what's going to occur, right? And so you cannot change any part of that system. It is no longer part of that tested system, right? What you're doing is you are then using a material, you know, it could be plasterboard, you know, lining, without a material standard. So you're acting outside of AS36 acceptable solution, and you're acting outside of a verification method. You know, there's how are you going to justify that? So yeah, no, I'm more inclined to put a hard no onto that one. Don't do it. Sorry, Michael, a slightly harder line than you take there.
I think that's fair, because we the road that I was going down there, and most of the systems that I would think would demonstrate the kind of behaviour we want would be a plywood shear wall on a system, or something that has some nail behaviour that we understand. At that point, you're designing a plywood shear wall, just use 3603. Yeah,
agreed.
Yeah, it's definitely an interesting discussion, and obviously the more I read these questions, I definitely think more needs to be done to provide answers. But I also have to say, engineers, when they design outside 3604, need to think like engineers and make some good solid engineering judgment, and especially the fact that brittle failure modes can occur, capacitance should be applied to some of these non-3604 buildings, definitely something to take into consideration. So we are slowly already over time, so I probably have 1 or 2 more questions for now, and then perhaps what we can do, the questions will be circulated, and maybe Mike and Mark and perhaps myself can provide some more answers to that. So one question which came up a few times was that a lot of houses nowadays have portal frames, and with the assumption that we now have a rigid diaphragm, what is a good way to define the relative stiffnesses between the timber walls and the steel frame? So there's probably many ways how to address that, but maybe Mike, if you can provide your thoughts on this relative stiffness problem between P21 tested walls and the steel portal frame.
Yeah. So I mean, for the portal frame, I think that's relatively simple. It's what we do almost every day on steel designs, and we can come up with a lateral stiffness of the steel element very quickly. If we're mixing that with walls, it requires a bit more consideration as to what an acceptable displacement is. If you have quite slender walls, which are quite flexible, you might be able to push the displacement up a bit higher. But if you've got very squat walls, you're going to have a very stiff response, and then you also need to stiffen that steel frame to be representative, you know, closer to the deflection of that wall. I guess where the grey area comes in is we talked about when you're trying to derive the stiffness of a P21 tested element. It's not 100% clear, and it's probably been tested at a few lengths, and you have to then try and extrapolate the stiffness out, which is which is not so easy to do. There is probably an argument that at ultimate limit state, you could use the center of strength of the system to define as a way of checking the overall torsion. So you have an approximation of the capacity of the wall, and you could have a look that way. Sorry, so it's a little bit vague because there's a lot of factors which would go into obviously figuring that out. Obviously, but
my suggestion there, because this is the reason why I put together that portal frame design guide in 2020, I think it came out, was because of exactly these sorts of questions. Angela Liu addresses, most of the questions that we have inside SR 337, but there's all sorts of things that we don't and can't really factor, damping, system damping, for example, and how are you going to be taking that into account? And you can either go down a relatively complicated manner, or you can simplify it quite a lot. And so when I put that guideline together, what we did is we said, okay, well, let's keep it at a fairly simple level and make certain assumptions throughout there. And that is in fairly widespread use throughout New Zealand. And if you're just going to be doing a two-story, right, I want to put that caveat on there. If you're just going to be using a fairly regular two-story building with the top floor being fairly regular, then I'd suggest just following that portal frame guideline that we've got in the website. It offers a pretty robust, simplified way of doing things that we discussed with experts from all throughout New Zealand, including Angela Liu and so on and so on and so on.
Thank you. I've popped in the link to this guideline onto the chat. I hope it comes through. So it's definitely a good reference to look at how this all work together, because there was also a question about the 1% drift limit. Now, very last question for today, otherwise we won't stop. Mike, when you talked about the example, you did talk about different ductilities in the sample building you were showing, and there's a lot of questions about mixing ductilities on a single building. Also because the actual guideline, the P21 in Engineering New Zealand guideline, also talks about, for example, having first level, ground level being SED with a ductility of 1.25 and then a higher ductility further up. Maybe you can just provide some more thoughts on the different ductilities in the example you referred to.
Okay, so
a specific page.
Yeah.
So is the question around assigning different ductilities to different levels? Is that the?
Well, there's several questions I'm trying to summarize. One is how can you mix, or how can you apply equivalent static analysis by having different ductilities is probably the first question. The other question, which I haven't mentioned now, is like, how can you select an adequate ductility? In terms of, is a ductility of 2 prescribed, or is it a choice? And obviously that's a much bigger discussion to be had. So I'm not sure if you want to go into that as well, but to start with, it's more like,
Okay, I'll probably start just by, I'll give you a little bit of thoughts behind the ductility of 2 that I mentioned there. That really comes from the slide that we were looking at before, where there's significant strength degradation in some plasterboard systems. And I say some plasterboard systems, it's not all of them. But as a general rule, if you were to not understand the background to it, I think there's the background to every single system that's being put into the building. The typical ductility of 3.5 that's selected for the NZS 3604 just wouldn't really hold true. It doesn't make sense. That is really something that you need to look at the product that you're specifying, and the way it behaves, and come up with a suitable level of ductility. As far as the selection, I mean, the other, I didn't really go into the ductility selection of the frames and the walls below. I mean, there's a number of ways you could approach this, and it's really the designer's decision. I mean, they could just choose to concentrate all of their ductility at the ground floor and then design the upper floors to remain elastic. They could allow some ductility on the bottom 2 floors and design the upper floor to remain elastic. I mean, there's a number of different ways to approach it. I think it just needs to be really well communicated by the designer in their design features report, how that's been handled.
When we were discussing this through the document, when we were putting it together, and there were a lot of discussions going on around this. And so I'm just going to really keep it down to the nutshell. But one of the things was, well, if we're doing a 3-story building, should we just refer through to the timber design guide? Because that tells you how to do it, right? But one of the things that they say in there is, you can do certain things provided that you've got a very stiff bottom story, which is, then allows you to do use certain assumptions going up. And it has to be, off the top of my head, and Daniel, you know this better than I do, 10 times stiffer.
Correct.
But that's very, very difficult to achieve in a lot of these houses, because that would really reduce your building, your construction materials down to reinforced concrete and masonry, right? And so then when we were talking about that, we got a lot of pushback from various parties, because it's like, okay, well, that's not practical. We won't be able to get these townhouses being built, for example, with reinforced concrete and masonry. It's just won't happen, right? And so how are we going to overcome that? Well, the general thinking behind this, with a very low ductility, on the ground floor, was that that's going to increase the loading on that ground floor, which inherently is going to increase the, because you've got your ultimate limit state deflection criteria. And what that means is that it's going to increase the stiffness. Okay, so by increasing the stiffness, what we're doing is we are trying to reduce the mode shape change, right? Going up through there, and keep it a little bit more in line with some of the assumptions that are being made with the loadings out of 3604. And then if you reduce or keep the ductility down to 2 or whatever else it might be, you're once again increasing the stiffness and increasing the loadings upon there. And as Mike was talking about before, then it's got those factors of safety and the system, going in there with the redundancies and so on. If you increase if you have in that ductility of 2, you're increasing the loading, and you're probably getting some of those system effects in there. Was the general thinking that we're putting in behind there, right? And so once you start to bring that back down to that general level, that's trying to get several meetings summed up in a few paragraphs, but that's why we suggested doing it like that. And I suspect that that's the same sort of lines that Mike's been working along as well, although I could be completely wrong, because we haven't discussed it.
Yeah, no, that's right. And I think also, just referring back to earlier on in the assumption, I think in 3604, that we can select a ductility of 3.5 for these types of systems, I think is inherently flawed, because of the very pinched hysteresis, low energy dissipation and whatnot. That reducing of the ductility is essentially just taking account of those things that don't kind of stack up with what we would normally do in design.
I think it's really valuable to have this discussion, because I think there's a lot of items which still haven't been fully addressed when looking at these multi-story timber buildings, and perhaps this could be an incentive for Engineering New Zealand, perhaps CSOC TDS, to continue working on a more detailed guideline moving forward, although it's a bit difficult to align all different thoughts, considering the different aspect to consider. Now, having said that, I would like to bring this meeting to an end. We're already over time. So thanks for all attendees who have stayed with us. Obviously, thank you, Martin and Mike, for your time and expertise on that, for the discussion as well. And we will try to get some of these questions further answered and sent back, and perhaps we can use them to maybe update or provide the second version of the guideline moving forward, once we also have the new version of NZS 3604 available, which should address, at least in part, some of the issues moving forward. So thanks, everyone. Have a good afternoon, and we'll see you back in a month for the next TDS webinar again. Thank you very much, and goodbye.
Thank you.